Okay, in this lesson we're going to look at equilibrium. Now, equilibrium is where all the forces balance out, so that there's no resultant force, which means the body is either stationary or it's moving with constant velocity. A few ways of doing it. One, it could be using a bit of GCSE mathematics. If we've got three forces acting in this way here, I've got two tensions acting at 40 degrees and 60 degrees to the vertical, and a weight of 20 G newtons acting vertically downwards. What I can do is, because I know it's in equilibrium, I can imagine redrawing all these forces one on top of the other, and what should happen is, treating them as vectors, they should start and finish at exactly the same point. So my diagram would look a little bit like this. If I took the T2 force first and drew it there, and then the T1 force like that, and then the 20G, I should end up back to where I started. So that length will be 20G, that'll be the T2, and that'll be the T1. My angles, because that's with the vertical, that's 60 degrees. T1's at 40 degrees there. Because we've got vertical lines there and the dotted one, that 40 is exactly the same as an angle there, which would be 40 degrees. And then by adding them together, 40 add 60 is 100. The one in between here is 80 degrees. Not exactly to scale, but it's a sketch. What I've now got is a triangle where I know all three angles and one of the sides 20G. If I want to find T1 or T2, I can use sine rule because I've got a pair. I know an angle and the side opposite. So to find the lengths, I'm going to use A over sine A equals B over sine B. Always have what I need, so let's choose one to find. Let's find T1, because 1's before 2. T1 over sine 60 equals 20G over sine 80. So T1 is 20G sine 60 degrees, don't forget, over sine 80 degrees. Press buttons, press buttons. There we go. I knew I had one of these somewhere or other. Use it every now and then. Check them in degrees, it's good. Fraction button, so it looks like it is 20 times 9.8 times sine 60, close bracket, divided by sine 80, close that bracket as well, equals 172 newtons. I can use up to three significant figures because I'm using G, which has got 2SF in. Remember, don't be too accurate. Just out of interest, because T1's up at the 60, that's the middle of the three angles. T1 should be the middle of the three forces. Don't forget 20G is 20 times 9.8, not 196. That's the biggest force because it's opposite the biggest angle. Do the same thing, quote the same thing to find T2. So it's T2 over sine 40 equals 20G over sine 80. So T2 is whatever 20G sine 40 is over sine 80. Don't forget these are in degrees. So fraction button, 20 times 9.8 times sine 40, close bracket, divide by, under there, sine 80, close bracket again, 127.9, 128 newtons. So in that case there, that's my smallest force, that's my middle force, and 20G, 196 is my biggest force, and it matches up with what I've got there. They look about the right sort of size in that case there. There's another way I can solve this one, and it's called by resolving. We've got to take in components both horizontal and vertical. That's mainly what I'm going to be doing for most of these ones here. So example 1, first proper example, has got a string of length 50 centimetres, it's got a weight of 80 newtons, it's attached to a wall at one end and a person at the other end. The person is being held away from the wall, 30 centimetres away from the wall because of horizontal force. There's a tension in the string, we need to find the tension. So here's my wall. What the 50 centimetres to the 30 centimetres are as a way of giving me the angle that the tension makes without giving me the angle. So I'm going to have a tension there. I'm going to have a weight, that should be vertically down. Vertical's not that vertical today. 80 newtons, and we've got a force F that way. Now, I could choose to find either of these angles here. I know that the distance, this distance is, well, I don't know what the distance is. I know that the length of the string is 50 centimeters. I know that this distance is 30 centimeters, and so by Pythagoras, that's 40 centimeters. Whether I need that or not, I'm not quite sure, because now, if I call my angle that I'm trying to be dealing with theta there, what I know about this is that sine theta is opposite over hypotenuse, 40 over 50, 4 over 5. 3, 4, 5 triangle. So cos theta, adjacent over hypotenuse, is 3 over 5. Now, if I consider this force T, that's going that way, and imagine splitting it up into components going that vertically and horizontally. I've got my theta there, there's T. What will happen in this case is this. This dotted line, the vertical one, is exactly the same as the one in the triangle there, which is opposite to the theta. The dotted line that's horizontal is the adjacent side to the theta, where T is the hypotenuse. So what you'll find is this. If I want to split this up into components going horizontally and vertically, this one going this way is going to be T times cos of the angle we go through, which is cos theta there. Now I'll say it again. Because cos theta is adjacent over T, the adjacent, when cross multiply, becomes T cos theta. This other one, I haven't worked out what theta is as an angle because it's not an exact one. But I've got exact values for sine and cos and tan if I need it. So it's best to keep it like this. I could work out what theta is, roughly 36.9 degrees. I could take it off 90, 53.1 degrees, and I could do the same there. I could say that the vertical line is T times cos of that angle. Now, that's great when I know what the angle is, but it's handy, as we'll see later on, to split up my horizontal and vertical components based on the one angle given. And it goes like this. If I've got it in my picture here, it's T times cos of the angle we go through. So yes, it's the same T times cos of that angle. What you'll find for this one, cos of 90 minus theta is exactly the same as T sine theta. So that one's going to be cos, the vertical one's going to be sine. And that's going to be useful because it allows me now to work out what T is. If I resolve, it's my notation to say what I'm doing, I'm resolving upwards, by which I mean it's in equilibrium. So whatever's going up, which is just T sine theta in this case, will equal whatever's going down, which is 8T. I know what sine theta is, 4 over 5. So T cross multiply is 8T times 5 over 4, which is 100 newtons. So T in this case is 100 newtons. If I needed to find F now, I could resolve horizontally. I could find F, which would equal to T cos theta, which will be 3/5 of 100, would be 60 newtons. Example 2 has got a plane. It's smooth planes, there's no friction, which is nice, but it is being held in equilibrium for some reason or other. So we've got our weight acting inversely downwards, a bit like we did in our drawing earlier on. I'm going to go dot dot dot, you'll see why in a moment. R for reaction, I've got 30 degrees here, like this. I automatically put in 30 degrees there. Okay, and in this case I've also got a tension holding it up, because without anything holding it up, it will want to slide down the plane. It's a smooth plane, so the weight component acting downwards will want to make it move down the plane. So I've got not a tension acting along the plane, but at 20 degrees there. So I've got my tension, and I've got 20 degrees there. Now, I've got got two angles in my picture, 30 degrees, 20 degrees. What I can do to help me with all my component work is this. I can use my sketch to show what the component of W would be along the dotted line. And as before, it's the force, W, times cos of the angle I'm going through, which is 30 degrees. That's why, whatever that angle is there, because it's 90 degrees there, that's 90 minus this. So there's also a right angle at this point. That angle there and this angle here are exactly the same. It's always the case. And so what I can say is that the component along the dotted line is W times cos of that angle, in this case W cos 30. What it means is, if I have to take components along the plane, it's not W cos 30, it'll be W sine. Similarly, the tension along the dotted line is T. There's the angle of 20 degrees in there, so it's T cos 20. And that's enough information to help me resolve to find T. Because I don't need R, so I don't need to go that way. I need to be resolving up and down the plane. And up the plane, as I've just written, is T cos 20. Down the plane is the component of W, which is not W cos 30, so it must be W sine 30. So T then will equal W times sine 30 over cos 20. Now, I don't know the exact value of W, so I can only write it in terms of W, so I'm going to do sine 30, close brackets, divided by cos 20, close bracket, equals 0.532, 0.53 lots of W. Okay, that's the value. That means it's in equilibrium, holding it in place at that angle there. Okay, last example then. Got a diagram with all these forces. I've got a 10 Newton force acting vertically downwards, got a 12 Newton force at an angle of 10 degrees to the x-axis, got the y-axis, got a force of F at an angle of theta, and a force of 9 at an angle of 30. And all the information is there. I'm going to help me out a little bit, do a few things. I'm going to do, as we did before, force times cos of the angle, 12 times cos 10 going that way. If we can squeeze in the two things here, I'm going to have 9 cos 30 going that way, and F cos theta going this way. And so I'm asked to find both F and theta, two unknowns, two equations. I'm resolving that way, and all the information is on the picture now. The 10 Newton force has got nothing going horizontally, so going this way I've got 12 cos 10, and that way I've got 9 cos 30 plus F cos theta. So F cos theta then will equal whatever 12 cos 10 is minus 9 cos 30. Now I'm going to resolve upwards. Everything's got components going up or down, so the two upwards are the F and the 12. Well, F. If that way is F cos theta, this is F sine theta. Similarly, if horizontally is 12 cos 10, this is 12 sine 10. Vertically, I've got the 10 Newton force, and then the component of the 9. If that was 9 cos 30, this is 9 sine 30. So what is F sine theta then? Equals 10 plus 9 sine 30 minus 12 sine 10. So I now know F cos theta, I now know F sine theta. It's really hard now to go on and solve these without combining in some way, shape or form. Two ways of doing it. I can, the best way, well, either way I'm using trig identities. I'm either using cos squared plus sine squared equals 1 from Pythagoras theorem, and do Pythagoras theorem on these two numbers, whatever they are, to find F, or tan is sine over cos, and that's what I'm going to do here. I'm going to write F sine theta as this, I'm going to divide by F cos theta, which is 12 cos 10 minus 9 cos 30, because what that will give me is what tan theta is. As you notice, I haven't tried to work out what these things are as decimals, because in doing so I would have to round off and possibly lose accuracy. I've kept them in terms of how they look, so 10 plus 9 sine 30, close brackets, minus 12 sine 10, close bracket, divided by 12 cos 10, close brackets, minus 9 cos 30, like that. Press equals to get tan, is where it is. Ooh, big angle. And then shift tan answer equals 72.0 degrees. So theta 72 degrees. And now all I've got to do to find f is do either of these. That's the shorter one. 12 cos 10 degrees minus 9 cos 30, and then divided by cos whatever my answer is there. So I'm going to use the answer button here for the angle and do fraction 12 cos 10 minus 9 cos 30 and there, and then divided by cos and close brackets equals 13.05, so f is 13 or 13.1 newtons. Check my figures, one significant figure, two significant figures. I could have gone to 2 or 3 figures, so 2 is fairly safe. I would not write 13.05. Don't be too accurate with your final answer. So notice I'm only using the buttons at the very end, and to avoid rounding errors I'm using the answer button to get as exact as I can, because it might have been, it might have wanted it to 3SF, and if I'd have rounded off I might have got 13.04 something and rounded down to 13.0 and lost the mark at the end. So be very careful there. So resolving, or a triangle of forces, if you've only got 3 forces, is a nice way to go, and use sine rule or cosine rule as appropriate. But take your time over your diagrams and look carefully at how you resolve your forces.